Hey there, everybody. So, our group is group one. We did the spread of diseases, more specifically the COVID 19. Now, in our presentation, we're going to be going over the models generally used to chart out the spread of diseases. We're going to go specifically over the models used for COVID 19 and the solutions behind all of them. Now, unless you've been living under the rock for the past 2 years, I'm going to go over COVID 19 a little bit. COVID 19 is a highly infectious disease, meaning it spreads from person to person very quickly. Now, this is why we had our 6 feet separation mandate a little bit ago. We have mask mandates. And the major problem behind it is that whether or not you are symptomatic, meaning that you could show signs of symptoms or you could not show signs of symptoms, and you could have COVID in both people. So this is why this was really important for all these mandates to come out. Now, some of the general, simpler models that are used behind the tracking of everything is the SIR, SIRD, and the SEIR models. Now, these are all made to chart out the spread of COVID, the spread of general diseases, and how we can try to figure this all out. Now, the first one we're going to go over, which is the most basic one, is the SRR model. Now, this is broken down into 3 parts. We have S for susceptible individuals, meaning these are everyone who can get the disease, who can get it really. The next one is going to be our infected individuals. So these are the people who have the disease in this model. And then our R is going to be recovered individuals. Now, this is going to be the most basic model for everything that we're going to see later on in this presentation. So our SIRD, so our SIRD, SEIR are this model, and then an added variable into it. And then you're going to see essentially this layout with additional variables for the final COVID model. Now, this is going to be the math behind it. This all plays, you can see all the derivatives and then the equations on the right side. Now, to see it in a graph, this is a real-time graph for a SIR chart. You can see the blue line is susceptible, which means that these are the people who can get the disease. You can see it starts off very high, and then as time goes on, it then drops. Now our green line is recovered, so you can see this is the exact opposite, or the inverse of it. And it starts off very, very, very low, and then goes to roughly the same point as the susceptible people. And then now our third one is going to be our red, which is our infected. And then this is going to be people who are infected. So you see a big spike in it at the beginning, and then it drops off. Now, when you hear the term flatten the curve, this is what that curve is going to be. So you can see it goes really high and then really low, and then essentially goes off to 0. All right, and now we're going to pass it off to our next person.
Hello everyone, this is Rodrigo, and today I'll be talking about the SIRD model for COVID COVID 19. So, the SIRD model is almost the same from the SIR that Jacob just talked about. The only difference is that it adds the D function that represents the function of death in the time of T. So, as you guys can see, it's almost the same thing from the SIR. The S from susceptible individuals, infected, I from infected individuals, R from recovered individuals, and D from individuals that die. You know that the function of death in the time of T. So, this model is very useful for diseases that cause many death, like the COVID-19, the Spanish flu, and the Black Plague, for example. All right. So let's move on to the COVID-19. So when calculating the using the SIRD model for COVID-19, scientists using a modified version that adds some functions of t. That is the A, that means the function of asymptomatic people or population that are people that were exposed to disease but does not show like any symptoms. Um, the function of C in terms of T, this means the function of confined people. So people that are cautious, like use masks, uh, you know, uh, make some distance from another person. Um, the E that are the exposed rate function. I'm sorry, not rate. The exposed people to the disease. Uh, and the Q that are the population that were quarantined in COVID. For example, we know that many people need to go to quarantine to not spread the disease so fast. So all these differential equations, they had some um, constants, as you guys can see, and they use the Greek letters. So I will explain to you what each of them means. You know, this alpha right here, it means the rate of subjects that become confined, people that start to become um, cautious with the disease. The beta is the rate of spread during contact. For example, a person that's not infected get in contact with a person that is infected. All right. Uh, this letter right here is the rate of comfort. I'm sorry, from the population that become asymptomatic. That means people that um, uh, were exposed to the disease but do not show any symptoms. All right, and this right here is the ERA. The ERA represents the rate of passive infections. That means people that were exposed to disease but do not like um, get in contact with another person that were infected. They were infected with, for example, the air or something like that. All right. So right here we have the T. That this is tall in Greek. It represents the rate of population that are asymptomatic and becoming infected. All right. This you guys can understand here that they are um, subtracting the rate by the time the people that are asymptomatic to know how asymptomatic people lasts. You know, this right here is the she. The she is the rate um, of the quarantine rate. You know, where people infectious people are going to quarantine to not spread the uh, disease. The alpha again and the um, this one here is the mu. The mu is a rate from confined to infected. People that were cautious but got infected by passive or not. Oh, sorry. This right here is the gamma. The gamma represents the rate of exposed that become infected. That means people that were exposed to the disease and already become infected. All right. So, um, and the last we have other two that are the lambda and this KD right here. The lambda represents the recovery rates of people that are becoming recovered from the disease, and KD is the rate of death. The rate in how death is going. So let's start. This is what those equations means. All right. So let's move on to a real example with a graph. This is a graph from infection of COVID-19 in China. All right. Each graph represents something for that equations: the number of infections by time, the number of deaths by time, and the numbers of recovery by time. All right. So let's see right here what we have. As you guys can see, this black line right here is the credits that were estimated. Okay, and this red one is what we actually have. All right. So if you can see right here, uh, the difference is like not so big. The estimated using the third model before the disease is was a very good um prediction, and the same goes for the number of deaths. However, the prediction were more bigger than really were. And the number of recovered was almost exactly just this gap right here, a little difference. Okay. Hope that you guys could understand. I'm sorry, my accent is very strong. So I had to talk a little slow here. Um, Now Jared will be talking about the SIER model. Okay. Thank you so much. Have a good day.
Exposed. So in the SCIR model, we have, um, the susceptible individuals, individuals that are, prone to getting infected but haven't been infected yet. And then we have a new piece here, which is the exposed, which it basically stands for you've been exposed but aren't infectious, right? You're not spreading it. And now we have infected individuals, which is, you're infected, you're able to spread it, and now and then the next part is the recovered individuals, which is, if you're infected, you either recover or, there's a portion of the population that die from it. And we're going to be using this DE for differential equation for the SCI model. So, the rate of susceptibles over time, which is, mu versus times n, which is the mass, the total mass population, minus the mu times susceptible, right? And these mu's are, constant rate, right? But now we look at this, which is the beta infectious times susceptible over the mass, constant rate. So it is at a negative trend here. So we're gonna see from a high standpoint, and then it's gonna just downward trend because there's gonna be less and less people that are susceptible because either they got infected or they got either exposed. And then we're gonna, on the next one right here, we'll move it to a positive, right? It's probably gonna go from an upper trend, at this DE, which is the exposed over time, right? So it's gonna go up and up, and then eventually it's gonna peak where this piece of this piece is gonna be subtracted by the exposed. So there's gonna be a downward trend. So there's going to be a peak, and then there's going to be a going downward trend. And then now we're going to look at the infectious people that have been infected, and it's going to be a constant rate here, times E, which is the exposed, minus the constant over infectious, right? So this is the infectious over time, and now we're going to be looking at the recovery over time. So we have gamma of infectious minus mu times recovery. So we expect, eventually all the susceptibles are going to go process from an exposed to infectious are going to recover. So this one is going to be going a downward trend, right? And the recovery rate is going to be at an upper trend. So we're going to see it in the next chart here, right? So susceptibles, right? This part, eventually all the population is going to be going at a downward trend, eventually flatten out here, right? And then we're going to look at the exposed rate, right? People that there's a latency, which either you're infectious or not, but not infectious yet. So it's gonna peak here. It's gonna go peak at this point, and it's gonna go downward trend. And now the infected. So these are people that are very infectious, right? It's gonna go at an upper trend, peak, and then flatten out, right? So this is the infected. But most importantly, at this time right here, hopefully we see, vaccines coming in, or a recovery, natural recovery rate, or, death, basically, right? So we would eventually see this up to uh, a, a, a recovery rate of a positive, right? So this line right here at the red line would eventually recover, hopefully just staying up here at this last part, right? At a high rate. Okay. So this is the SEIR model, right? This is the equation, right, for it, and hopefully you understand what it does. So conclusion is, we really want to understand the rate of disease like COVID-19 spread, because we want to implement like precautions. We want to understand, when the infection's going to peak, when, the volume of people are infected. We want to understand if there's going to be a lot of people at the hospitals. We want to prepare equipment, right? And we got to use the equation to understand, when we should implement, like, lockdowns, right? And we also want to use the math to tell manufacturing, when to expect, highly infected people, wandering out, so they can make safety equipment. And also the government needs to know when they should, when the curve flattens, when they should reopen public areas, like schools, libraries. And that's what the SIR model is for, that's what the CERD model is for, and that's what the SEIR model is for. It's for diseases like COVID-19. All right, and thank you. This is the last bit of our presentation, and have a good day.